So just like we can take the limit as x approaches a specific value, we can also take the limit as x approaches negative and positive infinity. And what these limits at infinity tell us is about the end behavior of the graph. So what's happening at the far left or the far right-hand sides of the graph. So we have three different possibilities for what our answers could be from these problems. The graph could approach positive or negative infinity, so it could grow without bounds. These could be bounded by a number, which means that the function has a horizontal asymptote, or it could just not exist. So a case where the limit as x approaches infinity would not exist is if the function oscillates between two different values. So you can think about the sine of x or the cosine of x graphs, right? Because they bounce between 1 and -1 out to infinity in both directions. So they're never settling towards a specific value, but they're also not growing without bound. So we just say that the limit does not exist there. So a key thing about limits at infinity is that they're the correct way of finding horizontal asymptotes. So in AP Calculus, if you're asked to identify horizontal asymptotes of functions, you're going to want to show proper limit notation to do that, even if you know with your algebra tricks, or maybe like your Algebra 2 course, what those horizontal asymptotes are, especially for those rational functions. So let's first practice just finding horizontal asymptotes without a calculator, well, aka just doing limits at infinity without a calculator. Right, so we take the limit as x approaches positive infinity of this cubic function, right? We really want to look at the leading term. So our leading term here is +3, and we have x to the 5th, so it's an odd graph. Oops, I don't know why that just switched my pencil tool. Okay, right. So if it's an odd degree graph, like a quintic is, and it's positive, that means as we go to the right, it might look something like this, and then it's going to go down on the left. So we're going to have positive infinity as x goes to infinity, so as we go to the right, and then in number 2, as we go to the left, we're going to go down to negative infinity. Right? So I kind of usually like to sketch some pictures when I'm dealing with these because it helps me keep all of the information straight in my head. So if I have the limit as x approaches infinity of e to the negative x, okay, so e to the x, right, looks like this. And then e to the negative x, well, that's just a flip around the vertical axis, so that's going to look more like this. So as x approaches positive infinity, our graph is going to 0. It has a horizontal asymptote at 0. And if we were to do as x approaches negative infinity, we would say it's going to positive infinity. Okay. Right, so the limit as x approaches infinity of sine, right, I just kind of talked about that one, right? Sine is oscillating between 1 and -1 forever, so it's never settling on a specific value, and it's also not growing to positive or negative infinity without bound. So we're going to say that this just does not exist, right? If you want, you can also say oscillation, right, as the reason why. I think that's how you spell oscillation. I don't know. That's why I teach math and not English. So then let's think of this function. So the limit as x approaches infinity of 1 over x times sine of x. Well, we know from our limit properties that we can kind of manipulate this a little bit. So this is really like having sine of x over x. So I'm going to rewrite this as the limit as x approaches infinity of sine of x over the limit as x approaches infinity of x. So now we might be saying from number 4, well, the limit as x approaches infinity of sine of x does not exist, but the limit of this overall function actually does. So the limit as x approaches infinity of sine of x is going to equal, it's bouncing between 1 and -1, right? So all of the values of sine of x are contained between +1 and -1. And now if we think about what the limit as x approaches infinity of x is doing, right, that's approaching infinity. So as we are going further and further out along to the right side of our x-axis, our values in our denominator are getting larger and larger, but the values of sine are staying between 1 and -1. So you're essentially taking 1 and dividing it by a really, really big number. So the limit of this is actually 0. So what this function roughly looks like is, right, we have our normal sine function here, right, and then ooh, that was awful. Okay, let's try that again. And then as we go out, it's getting closer and closer to the x-axis like this. Ignore my bad drawing skills. But as you get further out in either direction, because you're dividing it by a huge number in the denominator, but your value in the top is just staying between 1 or -1, you're actually approaching 0 here. Okay, so let's see. Now we're going to show proper limit notation for finding horizontal asymptotes for the following functions. So let's look at arctan first. So to find our horizontal asymptotes, we're going to take the limit as x approaches infinity of arctan, and we're also going to take the limit as x approaches negative infinity of arctan. So now arctan, this is a graph you definitely want to be familiar with. They like to pull this limit out a lot because it's a nice solid value. So our graph of arctan actually looks something like this. Right, so it has two horizontal asymptotes. So it has one up here and one down here. In the values that they approach, as x goes to the right for positive infinity, arctan is approaching pi over 2. And as we go to the left to negative infinity, we're going to negative pi over 2. Oops. So those are the values of our two asymptotes there. So now here, right, we have two different rational functions. So you're probably thinking back to what you learned. I teach it in Algebra 2, so I'm just going to keep saying the Algebra 2 course, right, when you're comparing the degrees of the top and the bottom. So again, we're going to take our limit as x approaches infinity. I'm just going to write f of x here because I'm lazy and I don't want to write out the whole function. Actually, no, I'm not going to be lazy. I'm going to show you the proper way to do this. So we know what the answer is, right? We know that there's a higher degree in the denominator than the numerator, which means that overall our horizontal asymptote is at 0. And for rational functions, they typically only have one horizontal function, one horizontal asymptote, so it's going to be the same for both directions. But let's make sure that we know how to definitely do this. And this is really sloppy, so we're just going to start over with my handwriting. Okay, so we have the limit as x approaches infinity of 3x squared minus 8x plus 12 all over 5x cubed plus 4x squared minus 2. So now the trick for properly taking these limits and how to actually know why the answers are what they are is what we're going to do is manipulate this. So we're going to multiply into the numerator and denominator by 1 over the highest power of x that you see in the whole problem. So here we're going to multiply top and bottom by 1 over x cubed. And we're going to distribute that to each part of the fraction. Right, so we're going to keep our limit notation. So what that's going to be, right, 3x squared times 1 over x cubed is going to give me 3 over x minus 8 over x squared plus 12 over x cubed all over 5 plus 4 over x minus 2 over x cubed. So now as we take the limit of each portion, right, the limit as x goes to infinity of 3 over x, right, and anything like that, like those basic little rational functions, right, all of these are approaching 0. So these are approaching 0, and then that's approaching 5. So our overall limit here is 0 over 5, which we know is just 0. And that's going to be the same case for x approaching negative infinity. And you can use the same trick here. Right, so we have a horizontal asymptote at y equaling 0. I guess I should write proper answer over here, right? We have horizontal asymptotes at y equals plus or minus pi over 2. Right, and then we'll do the same thing over here for our last function. Again, we're going to show the proper way to do it, but you guys know what the answer is already because you have taken Algebra 2 and you have studied horizontal asymptotes before. So we have 3x to the 5th minus 8x cubed plus 12 over that same function in the bottom. Almost, except we're changing that to a 5th power. Right, so again, I would multiply in by 1 over, the highest power now is x to the 5th. Right, so now as I do that, I get the limit as x approaches infinity of 3 minus 8 over x squared plus 12 over x to the 5th over 5 plus 4 over x cubed minus 2 over x to the 5th. Now as we take the, right, with our limit properties, we know that we can take the limit of each individual part and then just kind of put all the limit values together at the end. Right, all of these with an x in their denominators are going to go to 0. But 3 and 5, the limit of 3 and the limit of 5 is 3 and 5. So overall, we get 3 over 5, right? Which we know from algebra 2, right? Because they have the same degree. So we're going to take the ratio of the coefficients. And that's why that rule exists, is because of this limit stuff that's actually happening behind the scenes, right? And that limit's going to stay the same as we go to negative infinity, right? Because all of the x's essentially cancel out, right? You don't have positive or negative 0. So our horizontal asymptote is at y equals 3 over 5. Now there are some more challenging questions that we can look at that kind of take our rational functions to a different level. And that's when we include radicals inside of our rational functions. So we have this function over here, number 4, 4x minus 2, all divided by the square root of 9x squared plus 8x minus 1. So now, right, we want to think about this as like, right, the square root of 9x squared is really 3x, right? Well, 3 times the absolute value of x. So we want to be careful here as we take our limits. So we're going to take the limit as x approaches infinity, in the wrong color. Why can't I draw arrow symbols today? Like, that's not great. Okay, there we go. Right, we have 4x minus 2 over the square root of 9x squared plus 8x minus 1. Okay, right. So we're not going to do like all of the like formal stuff that I just showed you. We're going to just talk about it with like logic. So we know that the limit of 9x squared, well, the square root of 9x squared is 3 times the absolute value of x. So we're really just looking at this portion to determine our answers. So it's kind of like saying we're taking the limit as x approaches infinity of 4x over 3 times the absolute value of x. All right, so I'm just going to write that off to the side, right? We got 4x over 3 times the absolute value of x. Now, because the x in the denominator is technically inside of an absolute value symbol, we can't just cancel them out. But they do have the same degree. So if we think about what's happening for those leading coefficients in the top and bottom, they have the same degree. So as we go to the right, 4x is going to stay positive, and 3x is also going to stay positive, right? The absolute value there won't matter because the absolute value of a positive number is still positive. So as we go to the right, our limit is going to be 4/3. But now as we go to the left of this function, that's why that absolute value piece is really important to remember from when we simplify nth roots. So now as we go to negative infinity of 4x over 3 times the absolute value of x, right? 4x is going to go to, right, that's going to be a very large negative number. But in the denominator, the absolute value of those negatives gets canceled out, and it's really like having a positive. So we have negative over positive, so we're going to actually get negative 4/3 here. Right, so it's still coming to a constant value because the degree of the numerator and denominator is still the same, but you have to be careful because when you take the square root of x squared, you actually get the absolute value of x, so you actually have 2 horizontal asymptotes here. So we are going to have 2 different ones, so we have horizontal asymptotes at y equals positive and negative 4/3 because of that square root in the bottom. So let's look at another one. So over here we have negative 2x to the 4th is our leading term over 11x to the 8th, right? So the square root of 11x to the 8th, right, whoops, get ahead of myself, right, is really x to the 4th times the square root of 11, right, just taking the square root of the leading term there. So we don't need the absolute values here because x to the 4th is always positive no matter what value of x you plug in, right? And the square root of 11 is just square root of 11, so we're just going to leave that alone. So as we take our horizontal asymptotes, we're going to use proper limit notation as x approaches infinity. And I'm just going to write f of x here, right? So if we think about this as we're going to positive infinity, it's really kind of like taking the limit as x approaches infinity of negative 2x to the 4th over x to the 4th times the square root of 11, right? So those are going to cancel out, and we're going to get negative 2 over the square root of 11. And because all of the x's cancel out, because you don't have those absolute values to worry about, as you go to the left and the right, you're actually going to get the same value. So this is going to be negative 2 over the square root of 11, or you can say that's negative 2 root 11 over 11 if you want to rationalize it. For AP purposes, you don't need to rationalize your numbers. It's a good skill to still have because multiple choice questions could have the rationalized version and not the unrationalized version, just something to be aware of. And again, since all of our x's cancel out and we don't have to worry about that absolute value issue like we did in the last one, we're going to get the same value as we go to the left to negative infinity. So here we're going to have horizontal asymptotes.